Hi everybody. Thanks for watching our video for the first day of Unit 4 concerning the topic of extrema or extreme values. And what you need to know, absolute extreme values, those are talking about maximum or minimum points on the curve. So first example that we're going to consider is y equals x squared. First, when it's defined on the domain of all real numbers. So we don't really have a maximum. This thing's going to go on and on and on forever. But we do have a minimum value. The smallest or the lowest y value that this function is going to get to is right here at 0. So the location, or the x value that is the smallest, is 0, the minimum value that we reach is also 0. When we consider on just the domain that's from 0 to 2, we call this a closed interval. So 0 is included, 2 is included, and we're looking at all the x values in between. When we just consider that, the smallest that we're ever going to go, or the lowest, the furthest down that our function will achieve, is at a y value of 0. So that point 0, 0 is our global minimum. Up here, I'll put a dot because this is a closed interval. The biggest that our function's ever going to be on this closed interval, where the maximum value that's achieved, is up here at 4. So 2, 4 is our global or absolute max. Something kind of weird and interesting to consider. If you've got an open interval, so notice that the 0 and the 2 in this case are not included. Open interval. We don't have a minimum or a maximum. The reason is because we're not including 2, so if I said, oh, the maximum is at the number that's right before 2, so like 1.99999999999, you can always add another 9 to that. So that's the reason that we can't really define what the maximum value is going to be. So that brings us to our first big and important theorem, the extreme value theorem. If f is a continuous function over a closed interval, so where the endpoints are included, then we could say that f has a maximum and a minimum value over that interval. So this only works for continuous functions defined in a closed interval. Down here we'll consider kind of 3 different cases. If this was my function, I've got my endpoints. Here, my endpoints, like this guy right here, is not the lowest value that I'm going to obtain on this closed interval. The minimum would occur down here. That point right there is lower than all the other points on the graph. So there's my minimum. My maximum up here. Again, not at an endpoint, but somewhere within the interval. Other cases that could happen, your maximum and minimum might occur at your endpoints. So like rather than having a maximum or minimum happening somewhere on the inside of the interval, the max is the endpoint and the min is an endpoint. Another case is where you have one of your extreme values, like here the minimum is occurring at an endpoint, but the maximum is occurring somewhere not at an endpoint, but within the interval. So we've seen global maximums, so like the biggest overall. We've seen global minimums, so like the smallest overall, but we also have local extreme values. And a local maximum is the maximum value within some open interval. A local minimum is the minimum value within some open interval. So take a look at the kind of 5 different spots we've got marked out here on this example. Think about which ones might be our global maximums and minimums and which one might be our local maximums and minimums. So pause the video so you can think. Pause it. You're not pausing it. shake my head. Okay, well, let's go ahead and do the great big unveiling. The lowest place that we get on this whole graph is down here. So this guy is our absolute minimum. It's the smallest value overall. If something's an absolute minimum, it's also a local minimum. And let's maybe consider another local minimum, this guy. What it means to be a local minimum is, you may not be the smallest overall, but you're the smallest kind of in this little neighborhood. That guy right there is smaller than anything else around. You can see that happening at the other end point as well. So like this point is going to be lower than pretty much anything else around it, even though it's not quite as low as our absolute minimum. That would make those other two our maximums. So again, a local max is not the biggest of everything, but it's larger than the stuff that's just sort of in this little neighborhood around it. There's a local max. Absolute max means that value is the tallest, highest mountain of everywhere else on the function. If it's an absolute max, it's also a local max. So if you consider, like, what's the derivative going to be at all of these different places? At this local max, I might draw in a tangent line and see that that tangent line has a slope of 0, aka my derivative. I'll name this function f. My derivative is 0 at that local max. When I look over here at this local maximum, I see a cusp, meaning that my derivative is undefined or doesn't exist. And that's actually that piece of information is gonna help us with some of the problems that we're gonna be solving today. So, logical conclusion. Oh, check this out, Magic Ink. If you're looking for an extreme value, so like a local, global, maximum, or minimum, then the places you're going to need to look to find them are places where the derivative is 0, places where the derivative is undefined, or at your endpoints. Just so that you're comfortable with the phrasing in some of the questions that you're going to be asked, if the question says find where a maximum or minimum occurs, they're asking you for the x value. If it says what is the maximum or minimum value, aka how high up or how far down low do you go, that's asking you about a y value that goes with that x. And then if it asks you for the points, it's asking you for the ordered pair that represents your maximum or minimum value. Another word or vocab term that you're going to want to be familiar with is a critical value or a critical point. We're going to abbreviate them in like our notes as CV. However, that CV, don't write it on an AP exam. They'll be like, what do you mean? So a critical value is essentially just the places or the x values where your derivative is equal to 0 or where your derivative is undefined. So as we saw with our graph that was like this earlier, the critical values, so the places where the derivative was 0, like this guy, or the places where the derivative was undefined, like that guy, those relative extrema could only occur at our critical values or at our endpoints. So relative extreme or maxes and mins only happen at critical values or endpoints. Keep in mind though, maximums and minimum points in the interior of a function always occur at critical points, but critical points are not always maxes or mins. Example, if you've got y equals x to the third, right here, bang, I've got a derivative or a slope that's 0, but that's not a maximum or a minimum. It's not an extreme value. Same thing over here. I've got a vertical tangent line. My derivative is undefined, but I don't have a maximum or a minimum there. So we're going to have kind of an extra step in some of our problems to verify that these values are in fact maximums or minimums. No. Alright. If you're a person who likes steps for the problems that we'll be solving, here are some steps. I'll give you a second to kind of read over them if you want to take a look. I think they make a little bit more sense when you see them in the context of a problem, though. So we are going to be following these steps to answer the question on the following slide. So, if I am given a problem that says find the absolute maximums or minimum values for this function on the interval, keep in mind that maximums and minimums happen at our endpoints, or they can happen at our critical values, so the places where the derivative is 0 or undefined. Let's look at our endpoints first. We're only considering the endpoints because this function is defined over a closed interval. If it didn't have a closed interval, then you won't have any endpoints to check and you would just look at your critical values. So the endpoints for this guy are -2 and 3. So I want to see, okay, how high up does my function go at -2? How high up does my function go at 3? Take those guys to find the y values that go with them. We're just plugging into our original function, no derivatives yet. And I think it's going to end up being kind of gross and decimal-like, maybe. Let me check out my notes here. Yeah, so when I plug -2 into the function f, I get 1.587 as the y value that goes with it. When I plug 3 in, I get 2.080 as the y value that goes with x equals 3. So here are two possibilities. If I wanted to, I could kind of start sketching out my graph when I'm at -2. I've got this y value when I'm at 3. I've got that y value. So kind of starting to get an idea of like, oh, this one's bigger, it might be a maximum. Oh, this one's smaller, it might be a minimum. We won't be for sure, though, until we consider also our critical values. So I'll abbreviate those as CVs. Critical values are where our derivative is equal to 0 or where our derivative is undefined. Let's take a derivative. So f prime of x, oh, I'm so lucky, it's just a power rule, JTADDY, word. There's my derivative. It might be helpful for this to write it with no negative exponents, though. So cube root of x. Cool. I need to see, when is this thing going to be equal to 0? Never. When is this thing going to be undefined? It'll be undefined when the denominator is 0, and that's only going to happen at x equals 0. So this is a critical value, and from before, we know that this is a possibility for where a maximum or a minimum might occur. But we don't know for sure. It could be something like that cubic function where, oh, the derivative is undefined, but I didn't have a maximum or minimum there. So I want to check that out. And the way that I'll do that is by using a number line. Very similar to what we did with our investigation of motion problems. So I know that 0 is a critical point. That's where my derivative is undefined. Let's just see what the derivative is on either side of that, kind of get a better idea of what's happening with my function. I want to stay within my domain, or my closed interval, though. So I'm going to pick something between -2 and 0. Let's go -1. And I'm going to see what's the slope, or what's the derivative, what's happening with my function when x is -1. So if I take -1, plug it into my derivative, -1 raised to negative power, that's going to give me a -1 times 2/3 is still going to be negative. So I'm determining that my derivative at -1 gives me a negative answer. If I take positive 1 and plug it into my derivative. So take a positive 1, stick it in here. 1 raised to anything is 1, times 2/3 is just 2/3, so a positive number. What I'm determining by plugging into my derivative is that on the left side of 0, my function has a negative slope, or my function's going down. If I look at the values on the right of 0, I'm getting positive derivatives, or positive slopes, meaning my function's going up. So I'm going down, then going up. Down and then up, aka a minimum. So that's my way of checking that this critical value is actually potentially a minimum. So x equals 0, I'm going to add it to my list of possibilities over here. The y value that goes with 0, we're plugging into the original now, the y value that goes with 0 is 0 from my original function. So I've got another point that I can put on my graph. It makes sense what I found with this little number line when I consider the graph. Like, oh, I was going down, and then I was going up. So by looking at the graph, by considering these values, I see that the highest value that I get to is 2. This is bigger than the others. So this is going to be my max value. 0 is smaller than the others. This will be my minimum. So at this point, I've answered my question. I've found the absolute maximum. It occurs where? At 3. What is the maximum? 2.080. And I've also determined that the minimum is at 0, and the minimum value is 0. You can check this in your calculator, BT dubs. If you want to pull your calculator up, one thing I wanted to point out to you, when you're typing fractional exponents like 2/3 into your calculator, sometimes it's helpful to separate those out. So like x to the 2/3 means x squared under a cube root. Occasionally when you graph certain functions like maybe x to the 4/5, wink wink hint hint, your graphing calculator might only graph half of the function, so splitting it up into x squared raised to the 1/3 can enable your calculator to better get a picture of what's going on. The trace feature also allows you to see what y values go with particular x values. So like if you were feeling kind of lazy and didn't want to plug into the function, you could graph it and then do the trace and see, oh, the x value of -2 has a y value of 1.587. The x value of 0 has a y value of 0. And the other one we wanted to check out was like 3, I think. So you could scroll over and be like, oh, x value of 3 has a y value of 2.080. So that's the biggest one, that's the max. This is the smallest one, that's the min. What I want you to do for, I guess, quote-unquote, homework is A, come up with a list of any questions you have from this video, anything that was confusing. B, on the problem set 4.1 in your learning bundle, I just want you to try out numbers 5 through 8, so just those 4 questions, 5, 6, 7, and 8. They're on the back of the page. If you feel like you want to just go ahead and give them a try, quit the video, go do your thing. I'm going to work out number 1, and you could maybe use that as a guide to help you with 5 through 8, so you can just watch this part if you want to. It says find the extreme values and where they occur, then use your graphing calculator to sketch the function and verify your findings. Critical values occur at 2 places. They can occur at endpoints, and they can occur at your critical values. So endpoints are the easiest to kind of figure out what's going on. We're just going to take those and plug them into our function. Notice that here we only really need to consider 2. We see the hard bracket, meaning 2 is included. -1 isn't included, so it wouldn't be the place where our minimum or maximum occurs. So I'll just take 2, I'll plug it into my function, math, 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 boom, it's going to be 16. You can verify that in your calculator if you so desire. Cool, so sketch-wise, like let's put 16 up here. there's 1, there's 2, so we've got a dot up there. Critical values come from where the derivative is 0 or undefined, so I've got to take my derivative. Yay, power rule, JTADDY. And when I look at that derivative, I'm not going to be undefined because I'm not dividing by 0, I'm not taking a square root of a negative, I'm not taking a natural log of a negative. So I just need to figure out when is my derivative going to be equal to 0. So like when do I have a horizontal tangent line kind of situation? Because like a horizontal tangent line could be a place where I have a maximum or a minimum, potentially. Alright, so, how to solve. Factoring. So I'm going to take out my GCF, and then I'll set each of those pieces equal to 0. So my two critical values are x equals 0 and x equals 1. Now, just because those are critical values doesn't necessarily mean that I'm going to have a maximum or a minimum there. So I've got to make my cute little timeline and sort of see what's going on either side of those critical values. So my most favorite number on the side of 0, let's go with -1. So I'm going to see what is the derivative, or what's the function doing when x is -1. So I'll take that -1, bop, stick it up here in my derivative. So when I do that, so that would be -12 minus another 12, I get a negative value for my derivative, so my function's going down. Now let's check something in between 1 and 0. Let's pick maybe a half and see what's my function doing there in between those two. So I'll take a half, I'll plug it in up here to my derivative. Math. Hang on a second. I'm getting like a negative answer. What the heck? And that's okay. So my function's going down, and then it's going to keep going down, even though 0 is a critical value. Last one, let's see what's happening over here on the other side of 1. So let's check out the derivative, and let's go with maybe 2. So I'm going to take 2, plug it into my derivative, see what's happening, plug it in. I come out with a positive answer. So meaning my function is going to go up. If I wanted to draw kind of a sketch of what's happening, I could use my calculator to confirm this. Before I do, though, just sort of to interpret this graph, the y value that goes with 0, if I plug into my original function, is 0. And I'm going to have a dot right there. The y value that goes with 1, if I plug a 1 in to my original, I get -1. -1 is a minimum. My function had a negative derivative, so it was going down, and then it switched to a positive derivative, so I was going up. So when you switch from going down to going up, you get a minimum. So right here at 1, I will have a min. I was going down, and then I end up going up. But at 0, my function was going down, the derivative was 0, and then I kept going down. So this is kind of like that example we saw with the cubic function, where the derivative was 0, but I didn't have a maximum or a minimum. So when I consider my function, I've got an open circle over here, remember, at 1. -1's not included. When I look at this, I can tell from the graph that I'm going to have a max at 2 and a min at 1. I can also tell that from the numbers that I got. The y value for 2 was 16, or the biggest out of the 3, so there's my max. The y value for 1 was the smallest, of my possible values or possible places for maxes and mins. So 1, -1 will be my minimum. So I've, at this point, answered the question. I found my maximum and my minimum. The reason that I know I have to have a max and a min, because this is a continuous function that's defined over a, well, I guess I don't necessarily have to because it's not a closed interval. Trying to use the extreme value theorem, it just didn't happen. Anyway, give 5 through 8 a try. Come in with any questions, and we'll go from there. Good luck. Catch you later.